Welcome to today's lecture, friends. In this lecture, we will have a review of some important concepts from statistical physics which are relevant for this series, the thermal history of the universe. Now, the first important concept that we need to revise from statistical physics is the density of quantum states. And you may like to skip the derivation if you are convinced with the final result. The final result is that the density of states is given by G over H cube, and G, where G is the internal degrees of freedom, number of degrees of freedom, and H, if we H is equal to 2 pi H bar, and in the natural units, if we take H bar is equal to 1, so then this becomes 1 over H cube becomes 1 over 2 pi whole cube, and then the density of states, which is given by G over H cube, is equal to G over 2 pi whole cube. If you are convinced with this expression, then you may like to skip the derivation. Otherwise, let's go through all the steps. For a given species, each particle exists in one of the quantum states of that species. So for a given species, there are quantum states, and every particle of that species must exist in one of the quantum states. Each quantum state has its own momentum. So if there are n quantum states, there are n momentums. If there are infinite quantum states, infinite momentum. So every quantum state has its own momentum and hence its own energy level, because energy is a function of momentum. So if the particle of a species with mass m is in a state means quantum state, with momentum p, then its energy is given by this expression. Next, let us recap the definition of occupation number and the distribution function. The occupation number of a state is the number of particles in that state, and state means quantum state. The distribution function of a state is the expectation value of the occupation number of a state. So it is a function of the momentum, because a state is defined by its momentum. So for a given quantum state, the distribution function is denoted in terms of its momentum as f, as a function of momentum, and this momentum is the momentum of the state. Next, we want to know what is the density of states. Next, let us review from quantum mechanics a particle in a box, the famous scenario. Now, if we have a particle in a box, then the possible values for its momentum are this. This is a famous expression from quantum physics, where n1, n2 and n3 are integers, and this is particle in a box. So this is a three-dimensional scenario. That is why we have n1, n2 and n3. And in one dimension, for example, n1 goes from n1 takes the value of all integers, n2 is all integers, and the possible values for px, the momentum in x direction, are h over l, 2h over l, 3h over l. Basically it is n1 h over l, where n1 is an integer. So these are all the values of px, and note that delta px is equal to h over l. So in one dimension, the value of delta px, so this element, the momentum element in one dimension is h over l, and in 3 dimension we have the volume element for the momentum. It is given by h over l whole cube. So this volume element is h over l whole cube in 3 dimensions. So therefore the quantum state density in the momentum space. So in the momentum space we have number of states and number of quantum states divided by the momentum volume. And what is the volume element in the momentum space? It is given by this. So the state density in the momentum space is given by number of states divided by the momentum volume, and momentum volume, so there is one density per this volume. So one state, there is one state per this volume. So the quantum state, so the density of quantum states is given by one state divided by the volume, this, and we get L cube over H cube. Now we want to know that in the phase space, what is the state density? In the phase space, the quantum state density is given by number of states divided by the phase space volume. Phase space volume is now 6 dimensional. 3 dimensions are for the momentum, 3 dimensions are for this spatial coordinates. So we have delta x, delta y, delta z, delta px, delta py, delta pz. And what is delta x, delta y, delta z? This is L cube. So delta x and delta y and delta z, they are all equal to L, which is the length of the box, which is the dimension of this cubicle. L is the length, x, y and z dimension of the cubicle box. So we have delta x, delta y, delta z is the volume of the cubicle box, which is L cube. Then we have delta px, delta py, delta pz, and using this we get 1 over h cube. So the quantum state density in the 6 dimensional phase space is given by 1 over h cube. And in terms of h bar, this can be expressed as 2 pi h bar whole cube. Taking the natural units, in natural units h bar is equal to 1, and we get 1 over 2 pi whole cube. Now this is the quantum state density in the phase space volume, in the 6 dimensional phase space volume. Now if G is the internal number of internal degrees of freedom, for example, for electrons we have 2 spins, plus half and minus half. For neutrinos we have 3 flavors, tau neutrino, mu neutrino and electron neutrino. So G will be 3 for neutrinos, G will be 2 for electrons. So taking into account the number of internal degrees of freedom, the value of G, we get the quantum state density, the expression for quantum state density, the density of quantum states is equal to G multiplied by this. So which becomes G over 2 pi whole cube. Now let us look at some of the important expressions. So for a species with occupation number G and a state with momentum P. So let us focus on one state. For the first 3 expressions, these 3 expressions, the first 3, let us focus on one state with momentum P. So we are taking one species whose occupation number is G and focusing just on one state with momentum P. We have the particle number density given by the density of space, the density of states multiplied by the distribution function. Then for the energy density we have this expression multiplied by the energy of that state. Then for the pressure, again we have this expression G over 2 pi whole cube into Fp multiplied by the P square over 3E, which is the pressure corresponding to momentum P. Now to get the total value of the number density, energy density and the pressure for that species, for this particular species, is that we want to integrate over all states. So when we say all states, means we want to integrate over all momentums. So we need to take sum of these values corresponding to all momentums, so corresponding to all states. So these three expressions were corresponding to one state with momentum p. Now we are going to integrate over all possible values of momentum. So we will perform this integral to get these results for a species with occupation number g. So you see the difference. The first three were for one state whose momentum is p, and the next three are summing over all states. So summing over all states, we are integrating this expression with respect to p, and p is three-dimensional. We have dpx, dpy, dpz, that's why we have dqp. So summing these for over all states means integrating on the three-dimensional momentum space. For these three expressions, we get the total number density, the energy density and the pressure for that species whose occupation number is g. Okay, so this was a quick review of the density of quantum states, and we arrived at three important results. That's all for today. Thanks for watching. See you next time.